Today we're going to continue reading Gunning's An Introduction to Analysis, and today we're going to be discussing permutations and other tools that will help us develop the idea of the determinant of a matrix. An auxiliary tool is the idea of the permutation of a set of variables x1 up to x4, or in general, a permutation of a set of variables. You can think of it as an element of the symmetric group, which we considered earlier. That is, a symmetric group is the set of all rearrangements, so a particular permutation is one element in this set of rearrangements. Considering a polynomial, we can note that on top of the usual order, we can consider on the polynomial, which you can express p as a product of xi minus xj, you can consider another polynomial of degree n times n minus 1 over 2, consisting of the product of the difference of any two distinct variable, where the index of the first variable is less than the index of the second variable. That's this polynomial, to be clear. The square of this polynomial can be written as the product of all the differences xi minus xj of distinct variables, so it's independent of the order of the variables. After permutation pi of the variables, the resulting polynomial, which will denote pi times p of x or pi star p of x, still consists of the products of the difference of any two distinct variable, but possibly with the reversal of signs of the differences. For example, if you have p of x written in this way, as x1 minus x2, x1 minus x3, and x2 minus x3, then if pi is the permutation that interchanges the variable x2 and x3, the result of applying the permutation to this polynomial is x1 minus x3, because you switched x2 and x3, x1 minus x2, and x3 minus x2, which of course you see in this last term will switch the sign, since the first two were just rearranged, which is minus p of x. In general, pi star p of x is equal to plus or minus p of x for some sign, which is called the sign of the permutation pi, and denoted sign of pi, so that pi star of p of x, or pi star p of x is equal to sign of pi times p of x. A permutation is even if the sign of pi is plus 1 and odd if the sign of pi is minus 1. So you can also denote this by thinking about this as the, for instance, note that in the example we were given about pi, if our pi was switching x2 and x3, we note that that is exactly one swap. So a single swap of two elements will add a minus sign, or will multiply the sign of your permutation by -1. So for instance, after we swapped x2 and x3, if we swapped x1 and x2, then we could get a plus 1 by doing another swap. Note this should be minimal in the sense that we need to you could continue to interchange two elements each time, but that doesn't really do much, because every time you do two swaps of the same two elements, you'll get back to the same permutation, so it's going to have the same sign. But there are other ways of doing swaps between elements that are equivalent to each other, in the sense that they produce the same ordering of the elements, but the number of times you have to swap elements to form that final thing may be greater than necessary, so you always consider the minimum number of swaps required. We're going to have a theorem now, which is that the sign of pi is equal to -1 for permutation pi in this, if it interchanges xi and xj, which is what we just talked about. Any permutation can be written as a composition of permutations that interchange two variables, and finally the sign of two permutations is equal to the sign of each of them multiplied by each other for any two permutations. A permutation pi that interchanges xi and xj does not change the sign of any factor of the polynomial p of x that does not involve the variable xi or the variable xj. So for everything outside of that, this product is unchanged by the permutation. For elements between I and j, then the product of xi minus xk and xk minus xj is replaced by xj minus xk and xk minus xi, so the sign of the product is unchanged. Thus, the only effect of the permutation pi is on the sign of the polynomial arises when the change in the sign in the factor of just I and j, namely xi minus xj, which becomes xj minus xi. Hence, when you apply p star p of x, you get a minus p of x, so the sign of pi is equal to -1. That is, this argument just goes through every pair of elements and says, hey, are there I and j here? If not, nothing changes. If you have one of them, then there's a corresponding one where the other one is flipped, therefore you can just interchange those. And finally, there's the one with both of them, which has a minus sign introduced, so the sign in total is -1. Next, we're going to write that any permutation can be written as a composition of permutations that interchange two variables. So Suppose we have a permutation pi, which replaces the variables x1 up to xn by a rearranged set of them. Composing the permutation pi with the permutation pi1j1 that interchanges the variables x1 and xj1, replaces the variables xj1 up to xjn by x1, xk2 up to xkn. We can continue to compose this with another permutation that replaces the variables such that xk2 becomes x2. You do this continuously, and thus the composition of the permutations of pi with the composition of these permutations, which interchange them, leads to the identity permutation. Therefore, since we note that this is a group, that if you take the inverse of this entire product, you will get the final permutation. So the final permutation can be written as the inverse of these swaps, and then you see that the inverse of these swaps is each of the swaps, but in opposite order. Finally, for any two permutations pi1 and pi2 of the variables, pi2 star equals p of x is equal to sine of p2 by definition, and then applying the permutation pi1 to both sides yields pi1 star on pi2 of p of x, which is sine of pi2 times pi1 star of p of x is equal to sine of pi1 p of x by definition. On the other hand, if you do it in the opposite order, pi1 star pi2 star p of x is a result of applying first the permutation pi2 and then the permutation pi1. So is the result of applying the composite permutation pi1, excuse me, that's the dog, the composite permutation pi1 composed of pi2, and constantly pi1 star pi2 star p of x is equal to sine of pi1 pi2, the sign of the composed operation p of x, which suffices for the proof. This provides a useful way of determining whether a permutation is odd or even, which is what I talked about earlier, which is that any permutation can be written as a composition of transpositions that interchange two variables, while each transposition has a sign of -1, and the sign of the permutation is the product of the signs of these transpositions. It follows that a permutation is even if it can be written as a product of an even number of transpositions, and is odd if it can be written as a product of an odd number of transpositions. A permutation can be written as a product of transpositions in a number of different ways, but the theorem ensures that the parity of the total number of transpositions is an invariant of the permutation. With that, we'll continue next time with continuing to develop more ideas for the determinant, namely the idea of multilinear functions. With that, thank you for watching.